problems. And we will do it by maybe, I don't know if I will just give you a few examples for each trick, and then afterwards maybe we try to look at one problem in a more specific form and then reformulate it using our tricks. Okay? So we give it actually a name. So we make a chapter out of it, right? Later it will be a chapter. 16. And this improvised lecture will be dedicated to reformulations of problems. Yeah? So it will be about problem reformulations. And the basic observation that I would like you to note is that there are many possible ways to formulate the same problem, right? And they are equivalent one optimization problem can be formulated in many different ways. And some are actually easier for algorithms than others, and some are easier for you as a modeler than others, so it's good to know about all these things. Yeah? And I would like to start with a very obvious thing, and these are objective reformulations. So let's just start with objectives. What can you do with objectives? You can optimize a problem where you say, I minimize the function f of x, right? That could be a problem. There are many equivalent ways how you can state the same problem with exactly the same variables, and which will give you exactly the same solution. Maybe not the same value at this objective value, but think of what would be possible reformulations of the objective. So the objective is a function from Rn to R, and then what you could do with the objective is obvious, and I used it at some points already, but what could you do? You could actually map it through another thing, and you just say, this is equivalent, and I will not make equivalent because it's not really a statement, but it has equivalent solutions, and that's what we really want. So you could also minimize it if you send your objective through a function f of x. Through a function phi, where phi is what? It should be a function from R to R, and it should have some other property, namely, not Dimitri. Yes, convex, okay.
Monotonously increasing?
Absolutely, yeah. So it should be monotonously increasing, yeah. It should, if you want really uniqueness, then it should be monotonously increasing. Monotonously increasing. But it can be arbitrarily nonlinear, and depending also on the range of your function f, it need not be defined on the whole range. I mean, it could be if f gives only positive values, you could also have a function which is only mapping from the positive one. So to just give you an example for this, you could say, if I have a problem where you say I want to minimize the square of the square norm of x, subject maybe to some constraints like ax plus b equals 0, so that would be a nice, interesting optimization problem, right? This could be equivalently formulated as something which takes a monotonous function of that objective. For example, I take the square root of that, and then I have the norm of x without the square. This is a useful thing already if you look at this thing. So now I have two equivalent problems, ax plus b equals 0, but one of the two is easier than the other. Which one? The left, yes. Everyone agrees the left one. Why is it easier?
Because when you take derivatives, you can cancel the square.
Yeah, if you take derivatives, you can cancel the square. I mean, what you want to say is you can take the derivative here, right? Okay, and then it gets a linear system of equations. Okay, that's one point, exactly. If I formulate the necessary optimality conditions, in this case, we see actually they can be written down as a matrix equation, linear system, one iteration and it's solved, right? Also, this function is differentiable everywhere, while this has a non-differentiable point at 0. So also this would be a disadvantage. So we got rid by just taking, so to say, here we had square root, and sometimes people write it this way. And then you could just take the monotonous function x squared, which is monotonously increasing on the positive domain, and then it is getting you to this formulation. So this would be one example, right? Objective transformation. This is relatively easy, but you can, of course, do lots of other transformations. Maybe on the objective side, I would have some more things to say. There's one thing that I call the epigraph trick. So think of the 2 norm is okay, right? So that's a difficult thing, but it's not so difficult if you square it. But now what happens if I do something else? And the next thing is still under objectives, so it's 16.1, let's say. And so what we have here is what we call the epigraph trick. What I want to explain. I think I explained it already, but let's now make it more formal. So what happens if we have, for example, a problem like this? We have minimizing the 1 norm of x, for example, and I just subject to some simple equality constraints. So this problem has also some non-smoothness, right? Because the 1 norm is something which is actually the maximum of the sum of all the absolute values. Yeah? So you remember what is the 1 norm of a vector? X is the sum of the absolute values of the component of I. That's a non-smooth function at every point where the xi is 0. If where one xi is 0, this is non-smooth. So this is if you plot it, for example, in the 2-dimensional domain x1 and x2. This function is not only non-smooth at the origin, but it is also non-smooth on this axis, on this axis, on this axis, and on this axis. You remember the level sets of that? So if you look at all values where the 1 norm is smaller than 1, it's this diamond-shaped set. But the non-smoothness is basically the problem here at these points. So you wouldn't like that for optimization. You cannot even write down optimality condition. What can you do in this case in order to make it nice, smooth, KKT formulations possible? And there we use what we call the epigraph trick. And I can do it in 2 steps if you want. And the first one is something you can always do with any objective. Yeah? But here I start with an example. But I just want to make it, for this example, actually, I will go a few steps for the epigraph trick. So what I can always do, x is in Rn, I could introduce another variable t. And I just say minimize t. I call it t. T is a scalar variable, it's r. And x is in Rn. And I add another constraint to my problem, namely I have the original one. But now I add another constraint, and this says, so now I want to minimize t. Okay, but t is free, right? So what can be t? I could now set t equal to the objective. But equal to the objective is a very dangerous thing, and it will destroy convexity even for convex objectives. So we do something else. We do t should be bigger than the objective. That's a very funny trick, right? I mean, now the non-smoothness just did travel, but it's something that you can always do. And maybe before I go on, so this is not yet fully perfect, so let me just go on. On the way, so this is only one intermediate step, and there will be another step, but let's summarize what the epigraph trick in principle is, and why does it work. So I should have done that later. So what is the epigraph trick? It's just saying you have some objective, minimize f of x, subject to some constraints, which I can summarize as x in omega, right? So that's just something. And this is always equivalent to minimizing f t where t and x are now your optimization variables, where you say x in omega and t bigger than f of x. Can always do that. A short argument why. So the only thing you need to show for equivalence of optimization problems is that one problem, if x is a solution of one problem, then you can construct from it a solution of the other problem, and if you have a solution of this problem, you can construct from it a solution of that one. So that's what we could do. If we have a solution of this problem, we just set t to the value of f, and then we see that this should be a solution of that problem, because if the best f was achieved, then t can also not become lower in this context, right? I mean, for all x that are in omega, we have already found the optimal x, so t can actually, it's lower bounded by it. And on the other hand, if you have found a solution to this problem, then at the solution the t will have actually the best value of f, because if the t would be bigger than the maximum of f, I mean, if there would be a gap between these two things, so if t wouldn't be equal to f, then you could just reduce t a bit further until it hits the f, right? But if this f is not the minimal f, then you could now start to move the x a bit further inside the omega, so that the f gets smaller, and then the t could get smaller, and so you are not optimal. So it's very clear that these two things are equivalent, right? That's always the epigraph trick. The interesting thing is that the epigraph trick allows you to do some things like you can always make your objective linear. So you could also start to not think about objectives anymore, so to say, right? So that's why a lot of things we can also formulate in terms of constraints. To come back to this example, so this non-smooth example, we are not yet done. I mean, we have some problem here. We have still a non-smooth function, which is the sum of all these x's. So what we can still do is we can introduce new variables, which we call slack variables. So I continue with that example. So I add what we call slack variables because they are somehow additional. They are not necessary, but they express some slack between variables. So what we will get is actually, I will just introduce a variable which basically has the meaning, I call them S1 to Sn in this context for this example. And for this example we will now basically use them as if they would be Si would be the norm of Xi. So I do a lot of reformulations until I get to something nice and useful, but let's do it step by step to be a bit boring. So this, I give another name for this non-smooth dependence, so I call it just S, right? And now I could make my whole problem like minimizing T, element in R, S, element in Rn in this case, it's the number of outputs I have, X element is also in Rn, and then here I have now this, the T, then I have subject 2, ax plus b equals 0, and then I have all these constraints. The first one was actually t bigger than, and now I take the sum of all the si's by going from 1 to n. So that is clear, right? And now these si's are actually added. So I can also, instead of having this equality, I will just say si is bigger than the norm of xi. I could do that, right? The absolute value of xi. And this should hold for I going from 1 to n. So this would be an equivalent problem, which is still not having everything resolved, but it's already getting closer to something nice. So what you see is linear objective, linear constraints, linear inequality constraints here. This one I will really see later. We can remove it again, I see now. But anyway, it's just a lot of reformulations. And the S, because they are all positive, I can also have them with equalities here. The same argument that we had before. Yeah, so if the T is minimal, it will be pushed to all the sum of the S's. If one of the S's would still have place, it would get smaller, and then the T could get smaller and the objective would be smaller. So you see that these inequalities don't hurt us. So in a sense, it's twice the epigraph trick. But what we now observe is still a non-smoothness here. And now there would be a bad and a good way to reformulate it. So one bad way would be we say, that is interesting. So we just need to somehow the square of s should be bigger than the square of x, right? So that would be also equivalent to that. Sounds like an intuitive idea. Everything is nice, and we could still constrain the s to be positive, so to make it. But that's not going to work because it will violate LICQ. Yeah, so let's say bad idea. Si bigger than 0 and si square bigger than xi square. So we could just introduce these constraints. They seem to be equivalent, and they are actually equivalent. Yeah, this is equivalent to saying s should be bigger than the norm of x, but it will lead to LICQ violations. And I will not prove it here because, but it's easy if you go at the point xi is equal 0. You will see it at xi equal to 0. If this constraint is active exactly, then it's you would like to have LICQ, but then it doesn't work. So it's a bad idea. Good? Bad idea. Good idea. If s should be bigger than the norm or the absolute value of xi, what would be another equivalent reformulation? So what is the set? Here I have s, here I have x. Let's give it at the index xi and si. So s bigger than the absolute value of x is actually this thing, and this thing, and this is excluded, and that is excluded, right? So all these pairs of si and xi are compatible, that are above that. That's actually the constraint that says si bigger than xi, no, absolute value. And now if you draw it already like I draw it, then you see directly that this is equivalent to two inequalities, namely, so this is now really an equivalent, so I could say si is bigger than xi. That's what this inequality says. Si should also be bigger than this inequality, but that is minus xi, right? And then we are done. So we will actually now formulate the equivalent problem, and I realize because the sum of si's is a linear thing anyway, and I want to get a linear program, so I will do something stupid. I will eliminate t again. I didn't need that. That was just because it's an unprepared lecture. Yeah. Eliminate t because it was useless. It was useless here. But add these inequalities. Add 2n inequalities. And what we get now is the problem where we have minimizing s and x, and we minimize now the sum of the si's, and our constraints are ax plus b equals to 0, and then si is bigger than xi, and si is bigger than minus xi for I from 1 to n. Okay? So this is still the example, but I use this example, so to say, to get inspiration myself on which tricks did we use. It seems that we didn't use the epigraph trick, really. We used it actually not at the place where I used it first, but we used it for this constraint somehow. We looked at the epigraph of that function, so to say. So it is an epigraph trick in some form or of the other, but maybe the better name would be that we replace a mux using inequalities. So and the reason for this is that so I want to observe one thing. I want to note that this thing is the same as the mux of x and minus x. Trivial, but this is actually what it is, right? So the absolute value of an x is the max of two smooth, nice functions. So this is the trick that we can generalize. And so the general trick is actually this one, that if you have some inequality where you say, if you have something like S bigger than the max over some index set I, let's say, of some functions fi of x, which could be also different smooth functions. Yeah, so let's say here we have 2 functions, but it could also be 5 functions or some finite index set. Then this constraint is equivalent, and this is generally true, to the constraints where you have S bigger than fi x for I element in this index set. So you can always do that. Whenever you have a max of functions, on the right side of the inequality, on the right side meaning that it's at the lower end of an inequality, so that this is basically a convex corner, I should say. Maybe I explain that in a minute. Then you can do it. So max smaller than. That's where you can do it. If you have a max bigger than, then you are lost. You cannot do anything. Yes?
Do we have some limitations for the f?
No.
Okay.
Yes. I mean, it's just, you just look, so to say, at the feasible set of something, and if you think of it, you can have, I mean, this, you have some f's, whatever they are, they can be non-convex and so on, right? So this would be f1, this could be f2, and this would be s, and this would be x. And then the set described by the s's which are bigger than the max is exactly the set of s's which are bigger than each single one. Also trivial, but it's good to know about it.
If we have a non-convex function in it, then our problem is also...
You will not get rid of the non-convexity then. Yeah. But we got rid of some of the non-smoothness. And this is now the beautiful thing that we have here. So what was exciting about that reformulation? We started with something which was non-smooth. It looked convex. Actually, the one norm is a convex function. So what we have here at the top is a convex problem, but it was non-smooth. We wouldn't know how to solve it. Here we know which class does it fall into, by the way. What optimization problem class is this? You can help me, please. It was from the introduction. We had some overview of different problem classes, and some are easy and nice, and some others. So it's definitely smooth. So let's say, so all the functions, this is smooth, differentiable with respect to s and x, right? So it's differentiable functions everywhere. So it's definitely an NLP, but it's something more.
It's an LP?
It's an LP. It's a linear program. Thank you. So it's an LP. Because we have a linear objective function, we have linear equalities, and we have linear inequalities. That's what is an LP. So we could use an LP solver, which are extremely fast in solving things. We didn't treat LP solvers, I should say, but you can, for example, solve it with interior point methods if you want. So there are more tricks. So I already mentioned the name slack variables. So slack variables are these extra things that you introduce in order to make some things easier. But you can also have a lot of other slack variables. So we can have slacks for inequality, with equality constraints. And in order to do so, I would like to do some exercise. I just give you an example, which was, I think at some point we had a problem which was related to stiffness. But you can find it in many other applications. So let me just say there would be an example where you have some implicit function where you say, actually I have some matrix equation in my model. So you have, for example, a model where you can assign thicknesses to different trusses, and then this will affect somehow the bending stiffness of something. When you apply a force to this whole thing, it will bend a bit, and the amount of bending is what you want to minimize, for example. And in order to know the amount of bending, you first need to somehow invert a matrix. So sometimes you have a model that is described, a model described by implicit equations. And these implicit equations, they could be completely simple and linear, for example, and you could have something like, you have a variable that I call y, and it is given by the matrix inverse of something which depends on our decision variables x to the -1 applied to some vector b. So basically, this is something that could come from your modeling process, because you have a model, a simulation function which does this thing. And then you want to minimize a function of y, let's say f of y, subject to this thing. So you have this, but then you could formulate the problem of minimizing some function of this result, b of x, and then you have an optimization problem in x. So this could be a nice, interesting formulation, and I think a lot of the problems that you came up with during your modeling procedure until now had some way of implicit thinking here. Sometimes you use even algebraic reformulations to eliminate things, but in the more general case you could say this is like a linear system of, somehow I need to invert a matrix in order to get my some things, and then I put them into an objective function. And you obviously see how you can reformulate that, I hope. What would be the trick? So this is equivalent to a problem where I do x, but I also introduce another variable, which is actually y, in the appropriate space. I will not specify it now. And I just have f of y subject to, what should I do now? So I have this ax, a to the -1 times b. A is a matrix, b is a vector. I just stop you a bit because it will not be an inequality constraint. I don't know enough about the y and if they are monotonous or something. So this f of y could be anything. Just some objective of y. But I need to define the y, right? I could define it like this. Of course, that would be the most obvious way, right? I could just say y equals ax to the -1 b of x. Looks ugly. A is a nice differentiable function. B is a nice differentiable function. In principle, the matrix inverse is also a nice differentiable function, but it's maybe not as nice as the function itself. For example, sparsity is lost completely if you had a sparse matrix and so on. So, what would you do? Formulate this with an equivalent equation, right? And multiply it with A, because A needs to be an invertible matrix anyway. So I get it on this side. And now I have a constraint. And it's a nice and beautiful constraint, and I don't need to call my computer algebra package to actually compute first the matrix inverse as a function of x, and then also put this matrix inverse into my algorithmic differentiation tool to differentiate it. Of course you can do all these things, but it's so much easier to just formulate it directly with your matrix A here, and then the optimizer will do the inversion for you. Yeah. So basically, a rule that I would like to give to you is, so to say, make implicit function or keep implicit functions implicit. And the advantage is easier to write down and to compute derivatives, easier derivatives, and very often more sparsity. I don't know if you ever looked at just an exercise, e.g. if you have a matrix which is your A of x, would be something tridiagonal. And then zeros everywhere else. This is a nice sparse matrix, could have lots of sparsity. Do you know how the inverse of this matrix looks like? I don't want to write it down, and I don't know exactly how it looks like. The only thing I know, and you can test this easily in MATLAB, just make a random tridiagonal matrix, invert it, it will be full. Everywhere. Which is really a nasty thing, right? By the way, the LR factorization or LU factorization of A is still sparse. But once you actually really compute the inverse, it stands. So that's just something here. And this can be also done also for nonlinear equations. So if you have an implicit function where you say, so to say, g of y and x equals 0, and this allows you basically to get y as a function which I call h of x, where you have basically g of h of x comma x identical to 0 everywhere. So if you have some function f that is implicitly defined by such a thing, then you would always do it in optimization. You would just say minimize f of y subject to g of x and y, of y and x equals 0. So instead of, that is equivalent, of course, I didn't want to use it, right? So I don't do it. It's equivalent to, say, minimize x, and here we have f of h of x. So these two would be equivalent problems if you have an implicitly defined function. So instead of doing a lot of algebra, you could also just keep it in the implicit formulations. I want to give you one example where I found this very useful. Imagine you want to I give an example, and that is the example. I'm throwing a chalk. Yeah, so I just throw this chalk, and I have a certain height, and I want to find the right angle with which it will fly as fast as far as possible to the left. Right? So I would just throw it like this, and then okay. The chalk is broken, I need a new one. Sorry. Okay, but we have a height, h, then we throw the chalk in some angle, but I'm actually not so much interested in the angle maybe, or I can recover it later. So, and then the chalk flies, and at some point it will hit the ground, and I want to maximize this distance. So maximizing we know is minimizing, so I don't need to have this thing. But what would I do? I just know a few things about my motion, and I know that somehow the laws of motion are in the x and y axis. So I just maximize distance. And sorry, here I should say that my velocity has a Vmax bound, right? So I have a throwing velocity which I'm bound. Maximize distance thrown. So there could be, of course, there are many other formulations, but I just want to give you one formulation which I find particularly easy and which makes use of this implicit function trick. There will be others. And maybe you come up with some even simpler formulations for this particular problem, but let me just use it. So I know that there's some equations of motion which say x dot dot is equal to 0, but there's no gravity in this direction. Yeah. I also know that y dot dot is minus g. All okay, right? So from this I get basically that x of t is equal to x0 plus the velocity at the beginning, I call it v, vx 0 or maybe I call the two velocities directly. I give x dot I call u and y dot I call v, just to have different names, right? So then I don't need so many symbols. Then I know that this is, so to say, the velocity v times t, and that's it, because there's no gravitation, right? The other equation is actually that y of t is, I get from y0 plus u0 times t, and then it's minus 1/2 g times t squared. So this is another equation. I know how things fall. I hope that you agree. I mean, I used a bit of physics, so to say, or differential equation solutions, but basically it's twice integrating this thing and using initial conditions for both x and for the velocities. Is this okay or not? I mean, I can always explain some things more. So we have somehow a behavior of how the ball would fly, and we have functions x of t and y of t. So what would be now the optimization problem, and how can I phrase it? I mean, what are degrees of freedom? I could now say I have a trajectory, and this trajectory depends on x0, on v0, on t. Actually, t it doesn't depend on, but actually, if I would look at the end of my period, then I could call it maybe big T or something like this, right? So big T would be the moment when the ball falls down, and what I want to maximize is the distance that it has. So what I want is actually, let me just formulate it, I want to maximize the x coordinate at the end time. So I call the end time big T, and what I want to maximize is actually x of big T, right? That's what I want to maximize. So now let me formulate this thing using some variables, and I want to basically minimize the negative of x big T, right? This would be one thing that I could formulate. But I don't know t, I don't know xt, and so on. So how can I proceed now? So this xt, I know now how to write it down, right? So let me just replace it by the expression that we had there. It was x0, and maybe I give new names to these things. So I just actually say x0, I call it x0, and y0, I call it y0, and I call it u0, and v0, I call v0. Yeah? So then I have all these initial conditions as if not with the time index. I don't like the time index anymore, right? So I replace this whole thing here. So just wanted to say, so this is of course equivalent to that, right? And now I use it, I get sloppy. Yeah. And this is of course not specified yet what optimization variables I have, but what would I do? Maybe you can also help me, but I just say what I want. I want to have a problem where I put this minus, and then I put everything that I had just derived, so it would be x0 plus v0 times the time of flight, and that's it, right? That was it already. So this is my objective. And at least I need variables x0, I need a variable v0, I need a variable big T. If I would just formulate it like this, it would give nonsense, of course. Right? So now I need to add constraints, and of course the obvious constraint is that x0 should be equal to x0 bar, some position at the beginning, and let's make things simple, and I just say it's 0. So I start at position 0. y0, I can set, how did I call it? H. It's the height of me. Okay, so this 0 I could also omit, but let me just make it explicit. So now we have this y0 here. We didn't get the velocities in, so do we somehow have to restrict the velocities? How can we restrict the velocities? So we also would say velocity v0, together the norm should be bounded by v max, that's what I said, right? So how do we express that? There are different ways, but one way would be that I say v0 square plus u0 square should be smaller than v max square, right? So I could also take the square root of the whole thing and then it would be equivalent, but then this would be non-smooth, so I prefer this one. And because when it's active, these two things will be, one of them will be non-zero, I don't get LICQ problems here. So this would be some constraints. So now it's already getting better, but it's far from perfect. So I don't know the time of flight, which is the thing that I want to maximize. So how do I define the time of flight? When does my flight end? When did the chalk break?
Yt is equal to 0.
Perfect. So we need to formulate that as a constraint. So I just say, basically, y big T should be equal to 0, and then somehow implicitly this defines the T. How do we do it? We could just, I will put that in brackets because we will not formulate it like that, but we will equivalently write directly this expression here, which is y0 plus u0 times big T minus 1/2 g big T squared should be equal to 0. And now we have an optimization problem which is, in my eyes, well defined, and actually my optimization variables are augmented by y0 and u0. And if you look at this, of course there are lots of things which are really, really easy to eliminate. So let's eliminate all the things that are easy. This was in a sense just lazy and it's okay, but let me just eliminate x0, which was 0, y0, which was h, right? And then we keep only v0 and y0, so then we can also, in this case, we can just equivalently write it like minimizing u0, v0, and big T, and then we have here minus v0 times big T, subject to, these things we have already eliminated by just setting the things to the thing. This thing we need to keep. So I have v0 square plus u0 square smaller than v max, some number. And here we put the right value already in h and then u. Okay, so we get h plus u0 times big T minus 1/2 g times t squared is equal to 0. And that would be the formulation that I would recommend then to send to the solver. Yeah?
There's a square missing.
Oh yes, thank you. There was a square missing. Great. To make it equivalent. So this is now the problem of maximizing the distance that I throw. And of course one could now easily refine the model. If you would have now a model with air friction and you have a simulation routine that gives you more accurate simulation results for this x and y, then you could actually use that simulation routine to still use a similar constraint to this one, and you could still solve this problem. Yeah. So it avoids you to, of course, if you look at this equation, it's a quadratic equation in T, and you can, of course, you can solve it, right? So you could just use what we in Germany call the PQ formula, and you get the solution for T, then you select the right root, the positive one in this case, you plug it in here, and then you have some objective. It's possible, but it's nasty, right? So you can also do without. Okay, so this was a few of the tricks, and there was a general procedure that I mean, this one is avoiding implicit functions, right? So keep implicit functions implicit. Don't try to invert everything, yeah? So make equalities help your model, right? So let me just say equalities help modeling. So they help you to model. So there are some other cases where you can work with augmented intermediate variables, and this is something we mentioned already in one of the exercises. We call that lifting, and it's another point. So I make a new box. You can always lift lifting of intermediate variables. It's sometimes good, sometimes bad, but it's always something you can do with long computer functions. So what you could do is whenever we have, and that's actually similar to these implicit functions, so if you have a function, let's say minimize f of g of x, for example, and then you subject to some function h of g of x, smaller than 0. Yeah? So you write down your functions for equalities and for inequalities and for objectives, yeah? And then you realize that somehow there are some expressions in your functions which give you the same thing. So then you would say, why don't I somehow reuse these expressions? Why should I write them twice in this function and differentiate that function, then write it in this function and then differentiate that function? There would be a somehow easier way where you have to write down less equations later on. And what would be this way? Think of y, yeah? And I would like to invite you to suggest a formulation and to guide me. So I write already min, I write x and y. And now someone of you could, what would be the objectives that I need now? I want to introduce some intermediate variables that basically carry the value of something, namely of g, right? So it should be f of what? Great. And what should be my constraints now? Sorry, y is? Is what? And what is between the two? Sorry? Who is for equal? Who is for something else? Okay, don't worry. I think equal is okay. The point is I didn't specify anything about if this f would be a sum of the entries of g, maybe, but also for the inequalities we would also need something, and then under some circumstances we could replace that with an inequality, but only under some. Maybe I should have started with that trick before I do all these others, but anyway, this was a non-ordered lecture, right? So there's one constraint still missing now? Actually, exactly. H of y smaller than 0. So this is a completely equivalent problem. And what we did is, so y is called the lifted variable. Because it was, anyway, it was implicitly already there in your functions, right? So you had something probably in this code, you had something which was already called maybe y, and you just make it explicitly into this problem. And this we can do in also recursively, of course, right? So I just want to give you this example because it's a funny one. When you have, for example, a constraint which would say x to the 16 equals 2, right? So if you have this constraint, this is actually nothing else than x squared equals 2, right? So you could also lift a lot of intermediate variables, and you could just say this would be equivalent to saying y1 is equal to x square, and y2 is equal to y1 square, and y3 is equal to y2 square, and then y4 is equal to y3 square, and then you say y4 should be equal to 2. So this set of equalities is equivalent to that set of equalities. Because they have the same feasible solutions. And it turns out that if you solve such a thing with the Newton method, I mean in this case it's just a root finding problem, but of course SQP or any Newton type optimization methods also linearize constraints. Turns out when you solve this with a Newton type method and when you solve this with a Newton type method, this converges much faster. because some magic in these Lipschitz constants is much better. So you intuitively see that this is an extremely nonlinear function. Basically, x to the 16 is something that goes like whoop, whoop, right? So extremely nonlinear. While this one is a lot of quadratic functions together, so it's nicer functions which get better approximated by their derivatives. So in some sense, it can even have algorithmic advantages to lift intermediate variables. It can be easier. So the two reasons is less text in the functions, in the functions here. So this would be the reason here. You have avoided double text in your functions, but it's also sometimes better convergence properties. I should say that you can construct other examples where you have worse convergence properties, so it's not always good. But usually it's good. Yeah?
Is it certain that the algorithmic differentiation can automatically recognize, or does it have to be explicitly told that?
There are no tools yet. So the question was if algorithmic differentiation could, so to say, automatically lift variables. Yeah? And in principle, you could decide to lift all variables that are inside some decision trees, and that is a choice that is done sometimes, actually. Computer algebra packages do it very often. I mean, if you use ample and you optimize equations, you write down equations, and all these equations are directly treated, everything as a variable, so to say. That's one possibility. There are other tools which hide it, and algorithmic differentiation would not make these optimization variables, but inside Kazadi, in this environment that we also use, there is some functionality which supports the lifting of intermediate variables, but you have to decide which you want to lift. And the decision is, of course, there is no good way to know if it's beneficial or not, other than trying or to reason a bit about specific problem instances. Okay, so we mentioned lifted variables, slack variables, the epigraph trick, avoiding inversions, and that equality constraints help modeling. So I think my list is now exhausted, but there might be some other tricks that I forgot. Or maybe you have some tricks that were mentioned already in the discussions with you. If not, then we just do a break now, and after the break we can still include one or two tricks and then do the summary. 10 minutes, 25 past, we meet again. Okay, I just realized we still missed one important trick that is very useful in applications, and that is what we call smoothing. Smoothing non-smooth functions. I already gave you one possibility, that is for nice max functions, you had a way to reformulate them away with these extra slack variables, right? So the question is how to make non-smooth functions smooth. And there was the only good case, the good case was something where we had an inequality of this form that we had before, where we just had something like 0 should be bigger than the max of some functions fi of x, right? I element in the index set. There we remember this was just using the set of inequalities that was okay, right? So that was as before. So you smooth them away, so to say, by just introducing a lot of extra things. So you say this is smaller than x, I for I element in I. So these two things would be equivalent, and then you got rid of the non-smoothness. But there are many other cases where you wouldn't be able to do this, and the nastiest ones are the ones, for example, where you would have, let me just say, bad cases. So many bad cases. So one would be the max of our functions fi of x is bigger than 0. Sounds like easy to write down, right? You don't see that this is nasty, but it is terrible. Yeah. So why is it terrible? If I let me just do it simple for one example. So if I have something that has a max of two variables, x1 and x2, for example. This should be bigger than 0. So what does it mean in this space? So here I have x1, here I have x2. So how would it look like? The max of x1 and x2 should be bigger than 0. So the max of x1 and x2 is positive here, right? Because the x2 is positive, it's also positive here. So all points which are possible are actually the ones which are here, here, or here. And the only impossible points are the ones here. Why do I find this horrible? Yeah?
Yeah, we can't describe it with inequality constraints.
Exactly. So I cannot do one inequality here and one here because it's not the intersection of two feasible sets, but it's the union of two feasible sets. That's the problem. And the real problem here is that this corner is a very non-convex corner, right? So this is like a very nasty non-convex corner. So this non-smoothness cannot be done with any of these tricks that we did before. On the other hand, I could also say, okay, if someone really, really insists this is necessary and my problem has it, right? So it's basically an OR connection between these things. So either one of the f's should be bigger or the other should be bigger. And they can also be both bigger. It's an OR connection. But this is not something which leads to nice inequality constraint sets. Convex optimization is lost anyway. But you could say, okay, we give up on convexity. Then you could say, okay, probably it's not really, the solution will not be in the corner, and then I can forget about it. That would be one way to deal with it. And you just say, cross my fingers, formulate that function, differentiate it when I can differentiate it, and hope that this point where it's not differentiable is never encountered. This would be way number one. There is another way, you can also smooth this function. And the smoothing is what I want to explain to you, but I will explain it in a minute. I would like to do something else. So what is if you have now f(ix) equal to 0? Also, it's even worse now, right? Because I get now this set. In the same graph, for the same example, I would get this non-smooth set of equations, and then I don't know exactly if it is, it could even be that the solution is in the corner, depending on which direction the gradient goes. So I should be taking care that if it's in the corner, then I have a problem and so on. So there are many ways to reformulate this. One way, in this case, for this specific problem, you could also add the inequalities that were nice on this side, inequalities, and then keep that also as an inequality, and then somehow linearize it just where you are, and then hope that this point is treated well. And sometimes this works. Yeah? So this is sometimes called a complementarity constraint, just for those that are interested in it. So they are non-smooth, non-convex, yeah. But somehow people sometimes try to solve problems with these constraints. But we also would get problems with LICQ violations. So let me say, so one possibility here is that you just say the max of the fi's of x should be smaller than 0, and the max of the fi's of x should be bigger than 0, right? This one you can make nice, yeah? And you will actually use this formulation instead. And this is bad, but you can cross your fingers. Yeah, so that would be a possibility. But if you do this, what would happen immediately? I mean, even if I'm at a nice point, like this point, I have now one inequality that says I should not be on that side, another inequality that says I should not be on that side. Yeah, so I have actually a positive and a negative inequality, right? What will be violated at this point? ICQ. Because I have one constraint gradient pointing in this direction and the other in this direction, and they are just opposite to each other. It's the same thing. So whenever I have equalities, so this was, so inequalities, bad inequalities and equalities are always bad, so then I will always get the LICQ violation if I do this thing. So it's, if you accept LICQ violation, you can do it, and some servers accept that. But usually it's a really dangerous idea. So what could we do else? And here comes smoothing. And you should only do it in the bad cases. Yeah? So for the good case, we have a solution. If it's a max of smooth function smaller than 0, everything is fine. But if it's something else, like a max that needs to be bigger than 0, or a max that should be equal to 0, and max expresses a lot of non-smoothness, so let's just go for the max for a moment. Smoothing the max. And that is not an equivalent formulation, but it's an approximation. So it's not equivalent, but it's just an approximation. And the logic is extremely easy. So if I have, let me just first draw a picture. So if you have something here, you remember that was one function, that was the other, and the max is the top, the sum of the maximum of the two, of course. I could think of something which might be slightly bigger, approximately the same, and maybe at this corner has something smooth. So I could basically do this thing. That's an intuitive idea, right? Another question is, can we always do it in some way? And there is one particularly nice function that you can always use for it. And that function, even as a convex one, so it makes some max smooth, but it keeps the convexity of the max, if there was some convexity. But usually if there is convexity of the max, you don't need the smoothing. But anyway, so there is a function that does that is called log sum x. Easy to remember. And it is sometimes also called the Kreiselmeyer-Steinhauser function. And of course it's long names, so you will call it KS function. Yeah, so that's another name for the same thing in a different community. And what this function does, it's actually something which you just say max of fi of x is approximately equal to something where you take the logarithm of the sum I, let me just say here is I from 1 to n. So you add up the logarithm, the sum of exponentials of your functions. F I x, and then you do something that is always necessary here when you add exponentials. I mean, f could be any unit. Let's say f is meters or seconds or whatever. So you cannot put meters or seconds into an exponential. So it's useless. You need some scaling, even if you don't write it. There is some scaling, and I call these things sigma. And there should be the same scaling for all, because they are, anyway, they must have the same units. And then I put a sigma here in front again. And that is now a magic function which has exactly this property that I wanted to have, and I want to argue a bit about this function and why is it a nice function. So it should have a sigma bigger than 0. That's the only thing. And the sigma is determining so to say, the size of the smoothing. Yeah, so that's somehow determining the size of the smoothing. So if you make a big sigma, your function will be very smooth but very different. And if you make a very small sigma, so this would be a big sigma, and this will be a very small sigma. So let me argue what happens if you make a very, 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 very small sigma. A very small sigma means that And imagine that the f's are all slightly different. So one is bigger than the others, a bit bigger than the others. So if you take something that is a bit bigger than the others and then you divide it by sigma, and sigma is very small, it will be not only a bit bigger than, it will be significantly bigger than the others. Then you put it into an exponential, so it will be tremendously bigger than the others because it's an exponential. Then you add it up with all these other things which are tremendously much smaller. So you add 10 to the 23 plus 10 to the 20. And then it's actually already only 1/1000th of it, right? So it's basically the other parts basically vanish after the sum. So only the maximum survived the sum then you take the logarithm, and because the maximum survived, you take the logarithm of the exponential, and then you get the f divided by sigma. You multiply it with sigma, and then you get the f back. And so roughly speaking, you get the max. Yeah. Now, if in the worst case all the f's are equal, then you get, of course, an error. If all the f's are equal, then what you get here, so let's say worst case, or I call it worst case, all fi equal. What you get then is actually the sigma times the log times n times the exponential of fi divided by sigma, and all the fi's are equal, so it doesn't matter which fi I take. But I get the factor of n because I sum over all of them. Then you see that the n is actually, you take the logarithm of n, here is a product. So what you get is that this is equal to sigma times log n plus sigma times log x fi divided by sigma, right? Which is log x of, so this is actually equal to fi, which was the maximum value, and this is sigma times log n. Okay, so if I have the sigma small enough, this will be a small addition, and this is this addition. So here, when all the things are equal, so to say, maybe I take different functions, but at some point these functions might be equal, and that's where the smoothing is most significant. And so the smoothing here is actually sigma times log, I called it m, I think, right? Here was m, so I changed it to big N, so this is now m. So you get some feeling about what the sigma means. If the sigma is 0, you really get nearly a perfect approximation. And now you can do all nasty things that you want with it. It's a smooth function. Yeah, so you can have equalities, you can have max, you can have bigger than 0 for that. And it might still be very non-convex. So attention, non-convexity is not resolved. I mean, non-convexity remains. You cannot remove it. So let me just say one example of students which had a similar thing, which I think I found it very nice. So at some point you had a finger. You say I have a finger that should hold an object, and this object should be out of a body. And this body they describe with inequalities, a convex body. But now inside would be easy, right? Inside a convex body, no problem, just a lot of inequalities. Outside is the problem. So when we do it outside, then, I mean, this thing can be here, or it could be here, but what can we do? And then we should somehow formulate it with, we cannot say it should be bigger than this, or bigger than that, so that's not nice. So what, you will see it in the project presentation maybe, I should just say. But here you can use the Kreiselmeier-Steinhauser function by just smoothing, so to say, this set to something that is similar but not equal to it. And then you can just say, this is one nonlinear function, and my finger should be out, or should be on the positive or negative side, and I don't care about the convexity, but you see immediately that it's a very non-convex set. So you see that the finger, even though I make it smooth, if you minimize something, that is, it can be on the left or on the right, and so this is very likely to have local minima that are not global. Okay. Were there other tricks that I forgot? Actually, we could smooth other functions. So what do you want to smooth? And I smooth it for you. A min. Okay, a min we don't need to smooth. Because if we have a smooth max, then we can also use it for a smooth min. Yeah? So for min of fi's, the minimum of fi's, if you can always write this as equal to minus the maximum of the negative fi's, right? So that is the same. So whenever you have this, you could just replace it by that, and then you see if it has the right sign or not. Actually, the min of some functions should be on the positive side, on the bigger side of an inequality, then everything is okay, because then it gets a concave. Don't worry. You get it all when you just use this identity. Yeah, and then you can also smooth the min. What else would you have? The signum function. That's a very nasty function, because it's non-smooth anyway, so it's not continuous. It's not continuous, so that's worse than not smooth. It's non-continuous, and a non-continuous function, we don't even know if it has a well-defined minimum. Not a priori. In some cases, yes, in some not. But if you still say, I want something which is approximately equal to that, what would you use then for this? Like, this is signum of x. How could we approximate that? And there are many ways to approximate it. One way, two ways. Yeah?
X divided by the square root of x of x squared plus x.
Okay. May I use a sigma square here? I like that for unit reasons. Yeah, it's what you call epsilon. I agree. So that's a nice function. How will it look like? For very big x, this will dominate the sigma. So it's actually x divided by the norm of x. It's this thing. What will happen at 0 itself with this function? If we are at 0, this is 0. This is 0 plus sigma, so it's 0 divided by sigma squared. Okay. So at 0, it's basically 0. That's nice. What's the slope at 0? So the slope at 0 is actually 1 over sigma. Because I take the square root of the sigma at that. So it's such a function here. And again, if I make the slope longer, then somehow I get the scale here is roughly sigma. So the scale where I really significantly deviate from my original function is again expressed by this quantity sigma, which has the same units as x. So that would be one very nice function. I like it. Of course, forget about convexity, right? Do you have other? These are sigmoid functions, by the way. They are very popular in computer science, in an area that got very hot in the recent years again, after some sleep for 2 decades, I think. In neural nets, sigmoid functions are used a lot. Yeah. So I just CF neural nets or networks. But actually, in many cases, people use other sigmoid functions. So sigmoid functions, this would be one example. But there are others, and they all have this scale parameter that I call sigma. Yeah?
Is there a delta function in practice of this?
Delta function?
Yeah, so the derivative, say.
The derivative of that thing?
Yeah.
You want to have the derivative of that?
Yes.
Okay. I don't want to compute the derivative, but the...
Is there an approximation for it? Like this one?
Yeah, that's a very funny thing. So the suggestion is, if I would have an optimization problem where I have one of the functions which is even nastier than discontinuous, I mean, it's getting worse and worse, right? So we started with smooth differential functions. Then someone said, yeah, let's have, or I said actually, let's smooth kinks away. Non-smoothness, not differentiable. Then actually one of you suggested already have jumpy functions, which have, this is not even continuous, right? And now you suggest a distribution. Okay, that's like the nastiest nonlinearity you can imagine. But of course, even a delta peak function, in principle, you can smooth it, and you can smooth it with a Gaussian if you want, or you can smooth it with the derivative of that function if you want, so then it will be a smooth function. And you can also smooth it, approximate it with the derivative of any other sigmoid function. And I just want to recall some other sigmoid functions, which maybe the computer science is something you might remember or know. Yeah? Sorry?
I remember the exact function.
Yeah. So one possibility is also the tangents hyperbolicus, of x, which is actually, what is it? It's the tangents is usually sine divided by cosine, right? So it's sine hyperbolicus divided by cosine hyperbolicus, which is, what is it? It's the exponential e to the x minus e to the minus x divided by 2, divided by e to the x plus e to the minus x divided by 2. So these definitions. So the 2 is getting away, and we just get e to the x minus e to the minus x, and then e to the x plus e to the minus x. And of course, again, we have an exponential of an x, so I don't like that. So actually what you should use is tangents hyperbolicus of x divided by sigma. And then it's unitless, and then you can have something where you have a reasonable measure of where you smooth. And the sigma is, of course, something you should choose. So never forget the sigma. And then you have here e to the x divided by sigma minus e to the minus x divided by sigma, e to the x divided by sigma plus e to the minus x divided by sigma. This function is something I like particularly, and I want to just point out one thing. If you just take this factor out, you can also get to a different formulation. I mean, I multiply everything with the inverse of that. Yeah, then I could get here a 1 minus e to the minus 2x divided by sigma. And here I get a 1 plus e to the minus 2x divided by sigma, right? And I get a completely equivalent function, but I just wanted to tell you. What I could now get is actually I make a plus and a minus sign here, so I just add this thing and I subtract it again. Okay, just for fun. And what I get is, actually I summarize this and that with this and that, and then I get actually a 1. And then I keep plus, actually minus, is it minus? I think it's minus e to the minus 2x sigma divided by 1 plus e to the minus 2x sigma. I think until now I didn't change anything, right? Should be, sorry, and the factor of 2 was missing here, exactly, thank you. Okay, and exactly, what I can do to simplify it further is I multiply this whole thing again with the inverse of that to make it even simpler, and then I get 1 minus I have the feeling that I did an error somewhere, but I'm not sure, but let's do it at the end. Minus 1 divided, minus 2 divided by e to the 2x sigma plus 1. Right? I think that should be okay. It's still the same function. I just say it because in physics you very often have something like this, 1 plus 1 e to the minus x. So this is a very typical function that you see a lot in physics, and also in neural nets you sometimes see it. But it's with some reformulations. I mean, you see that I can just plug in this variable with a minus x here. So basically the tangent hyperbolicus and this smoothing function are the same up to some linear rescaling. So I just want to mention there is another form. I don't know what you would prefer. This one is a bit easier. I think algebraically you just have a little square and the square root, and here you have at least one exponential to evaluate. Okay, so this was smoothing for sine functions, which leads to what we call sigmoid functions. And derivatives of them, of course, are getting nastier and nastier. So I think I would not recommend to formulate an optimization problem where your objective is the delta function of some other function. Yeah, so it's just something that you better don't do because it is very non-convex. There are many reformulations that are possible and true and not very beneficial. Yes?
Do you recognize that your optimization falls into such a pickle? Something like that? Can you recognize that?
Yeah, exactly. We should make a science out of it. I think I recognize it in some cases and in some others I don't, but I'm not so sure how to formalize that. But I can just say a few things that, let me give you the intuition why, so to say, a delta function of some smooth function is a bad thing, right? So let me just say, I want to minimize somehow delta of, I still try to see if it really makes sense, but let me just see. So it's a delta, and I make a smooth delta approximation of some variable that I call just x. Yeah? X element in R. Let me just do this thing. It's of course, it's an extremely nasty function, right? So how does it look like? So my function f looks like this. It's this thing, and then it has a smooth thing, and then it's this thing again. So this is x, and this is f of x. This whole thing is f of x. So that would be a smooth approximation of a delta function, and of course there could be other things, but the main point is whenever I'm here there is no derivative of this function. It has no gradient, so it will not lead me down to anywhere. If I'm here at some point I will actually go to that side. If I'm on that side I would go to that side, so it's really non-convex by definition, you see, right? And this is something that you immediately feel like, oh, that seems to be very dependent on my initialization. So you formulated from the beginning a problem which was very, very non-convex, and actually it didn't have a solution, but after smoothing you might have a solution in the Weierstrass sense, but in the practical sense you might not. There was another remark or question. There's another thing that also I wouldn't recommend. I just wanted to say, if you have some constraint that x should be an integer, so then you could just say, hey, integer problems, no problem. Let me just introduce a constraint that says sine of pi times x is equal to 0. It's a smooth function. Pi is a nice number. X is my decision variable. And my function will have exactly the zeros at the integer numbers. Because pi times any integer is a 0 of the sign. So it looks like equivalent. It is equivalent. But what would be the nasty thing of this constraint? It's smooth. It probably has LICQs satisfied at this point. But why would I not like to, if you feed this now to an NLP solver, what would be the problem here? Sorry?
It would get stuck in the next
Yeah, it would get stuck in one of the two in the points. Actually, if you initialize accidentally in one of these points, it would get stuck in that point. If you initialize maybe here, it depends a bit on your other variables, but The linearization of that constraint will lead you here, and then hopefully you converge. Yeah, but you will actually just get into one of these many roots, and that's where you will stay, and your optimizer will not, your algorithm will not try among all the other possibilities. So it's actually, it's finding a local minimum in the strict sense, but it's a local minimum which is extremely much depending on your initialization. So you wouldn't like that. If you have an integer constraint, it's very non-smooth, of course. It's non-differentiable and so on. In reality, I mean, your x is just integer numbers, so you should just not use any nonlinear programming method, but an integer solver, and use mixed integer or integer programming, which also exists as a class and which uses very different methods than what we treated here. And they are efficient for convex integer programs. You remember that from the summary. But I think now we are over time already. We stop here and we do the summary lecture on next Tuesday. Okay? But in the meantime, and tomorrow afternoon at 4 o'clock, I would really invite you again, and I try to pop up there. I need to see if I think I will have time to pop in again to discuss the problems and your problem formulations, and hopefully some of the tricks of today help to make some things more elegant or more complicated or more smooth, easier to solve, and so on. Yeah, thanks you, and see you tomorrow.